Welcome to another class. In this lecture, I will be discussing about the velocity boundary layer and the development of the boundary layer for a flow over a flat plate and the different flow regimes such as the laminar, transition and the turbulent flow regimes over a flat plate. Consider a parallel flow of fluid over a flat plate, as you can see in this diagram. So this is a flat plate and the fluid is moving in this direction from the left towards the right. So the turbine blades can be approximated as the flat plates with reasonable accuracy when the fluid is moving through the turbine and when the fluid comes in contact with the turbine blades. So we can approximate the turbine blades as the flat surface when the fluids comes in contact with the turbine blades. So there will be different flow regimes such as laminar, transition and turbulent regimes, and we will discuss about these different flow regimes. So starting from the discussion, we will assume that this is the starting point of the plate and this is also the starting point of our xy coordinate. So x coordinate is measured along the plate surface from the leading edge of the plate in the direction of the flow. So this is the leading edge or the starting edge of the plate and the fluid is moving in this direction. So the x dimension will be starting from this point and the x dimension is increasing from left to right. Similarly, the y is measured from the surface in the normal direction. So at this point we can see that the y dimension is 0 and it's increasing in this direction. So this is the xy coordinate system. So the fluid approaches the plate in the x direction with a uniform upstream velocity which is known as v, capital V, and it is practically identical to the free stream velocity which is u infinity. Free stream velocity means it has no effects of the surfaces or the surrounding surfaces over the flat plate. So this is the free stream velocity which is of the fluid which is moving above the flat plate surface. For the sake of discussion, we can consider that the fluid to consist of adjacent layers piled on top of each other. So the velocity of the particles in the first fluid layer which is adjacent to the plate becomes 0 because of the no slip conditions, as I have discussed in the previous slide. So the layer which is adjacent to this plate will have 0 velocity and it will be considered as the motionless layer, and due to the friction this adjacent layer of the fluid will slows down the velocity of the above layer. So it means that the friction effect will become smaller as we move away from the surface. So the fluid layer which is adjacent to the flat surface will have the maximum friction and it will be considered as will have the 0 velocity as we move away from the surface. So the second layer will have the less friction and the third layer will have the less friction and the fourth layer from the surface will have the less friction. So it means that the velocity of the layers will be increasing when we move away from the surface. So the velocity profiles will be generated just like this one. So this is the velocity profile. So at this point where my pointer is, at this point the velocity is 0, while slightly away from the surface in the y direction the fluid will have some velocity. It will observe or it will face some kind of frictions due to this flat plate, when we move slightly away from the surface, the velocity of the fluid layer will be slightly higher, and if we move slightly away from the surface, the velocity of the layer will be slightly higher, because we are moving away from the surface, and the fluid layers which are away from the surface will be experiencing less friction, and at some point the velocity of the fluid layer which is far away from the surface will have the maximum velocity, and it is known as the free stream velocity. So at the start of the velocity boundary layer, so the fluid is moving in the streamlines, so this region will be known as the laminar boundary layer. The thickness of the boundary layer is different in different regions. For example, in the first region, the thickness of the boundary layer is from this flat plate to this point where the velocity is the maximum of the fluid, whereas in the transition region the thickness of the boundary layer is different, whereas in the turbulent region the thickness of the boundary layer is different. Basically, the thickness of the boundary layer, velocity boundary layer, is represented by delta. So the question is how this streamline flow will be converted into the transition region, and the transition will ultimately comes into the turbulent region. So it mainly depends on the Reynolds number. If the Reynolds number is higher than 5 multiply 10 raised to power 5, this laminar region will be transitioned into the region where the small eddies or the small disruptions will be generated, and ultimately these turbulence or the uneasiness in the boundary layer will grow in the turbulent region. The effect or the presence of this plate will be observed in the fluid up to some normal distance. So in the laminar boundary region, the presence of the plate is observed up to this point, right? And whereas in the turbulent boundary layer or in the turbulence region, the thickness of the boundary layer is observed up to this point. The presence of this flat plate is felt up to some normal distance in the y direction up to delta, and beyond which the velocity of the fluid will be simply known as the free stream velocity, which is u infinity, and it will remain unchanged after the boundary layer thickness. So as a result, if we say that this is x-axis and this is y-axis, so on the x-axis y is equal to 0, what does it mean? That the velocity on this flat plate of the fluid, or the velocity of the fluid layer adjacent to the flat plate at y is equal to 0 will be equal to 0, whereas the velocity of the fluid layer when y, that is the y coordinate, is equal to theta, this will become known as the velocity of the fluid will becomes the free stream velocity. So the simplest definition of the boundary layer is the region of the flow above the flat plate bounded by the thickness, this delta, in which the effects of viscous shearing forces caused by the fluid velocity are felt, is called the boundary layer. This is the definition of the boundary layer. The boundary layer thickness is simply represented by this delta and is typically defined as the distance y where u is equal to 99% of this free stream velocity. The flow on this flat plate is basically divided into two regions. The one is known as the boundary layer region, in which the viscous effects and the velocity changes of the fluid layers are significant, whereas above this boundary layer there is also the fluid which is moving from left to right, and this region is known as inviscid flow region. And we say that in this region, which is above the boundary layer, in which the frictional effects or the viscous effects are negligible, and velocity of the fluid which is moving from left to right will essentially remains constant. In the velocity boundary layer, we have three different regions: laminar, transition, and the turbulent region, and each region will have the different velocity profile. The velocity profile is approximately parabolic in the laminar region, whereas it becomes flatter in the turbulent region. The turbulent boundary layer can be considered to consist of three layers, as you can see in this diagram: the laminar sublayer, and it is very thin layer which is adjacent to the flat surface, where the viscous effects are very dominant. The velocity profile in this laminar sublayer is linear, and the flow is up to some extent streamlined. The next to the laminar sublayer is the buffer layer, in which the turbulent effects are significant but not dominant of the diffusion effects. And next to the buffer layer there is the turbulent layer, in which the turbulent effects are very dominant. The intense mixing of the fluid in the turbulent flow as a result of rapid fluctuations enhances the heat and the momentum transfer between the fluid particles, which increases the friction force on the surface and the convection heat transfer rate. It also causes the boundary layer to enlarge as the fluid moves in the right direction. Both the friction and the heat transfer coefficients reach maximum values when the flow becomes fully turbulent. So it will come as no surprise that a special effort is made in the design of the heat transfer coefficient associated with the turbulent flow. The enhancement in the heat transfer in the turbulent flow does not come for free. However, it may be necessary to use a larger pump to overcome the larger friction forces accompanying the higher heat transfer rate. As you can see that this is the flat plate, and the velocity of the fluid layer which is adjacent to this flat plate will be equal to 0, right? And this frictional or the viscous effects will be observed until the distance in the normal or the y direction will be known as the thickness of the boundary layer, and this will be the thickness of the boundary layer. So this thickness of the boundary layer will be represented by this delta, and above the thickness of the boundary layer the velocity is simply known as the free stream velocity, and this free stream velocity is simply the velocity of the fluid with which the fluid is coming onto this plate. And the thickness of the boundary layer is observed until the velocity of the fluid will be equal to 99% of the incoming fluid velocity. I think this is a more clear picture in order to understand the velocity boundary layer and the thickness of the boundary layer, and in order to understand the viscous or the shearing effects. So at the end I would say, after understanding this topic, the students must be able to understand that when the fluid flows on a flat plate, what will be the velocity profile and which layer of the fluid will observe the maximum shearing effect, and how the velocity profile changes in the y direction. So surface shear stress. It is an interesting topic to understand that consider a flow of a fluid over a surface of a flat plate, as you have seen that in the previous slide. The fluid layer is in contact with the surface, will try to drag the plate along via friction, exerting a frictional force on it. It can be seen that this is the fluid layer which is moving in this direction from left to right. When this fluid layer will move in this direction, it will try to pull this flat plate in this direction. Although the flat plate is fixed, it will not move, but this layer will apply some force on this fixed plate in order to drag in the flow direction. So in other words, this layer is applying a shear force on this flat plate. So the second layer will apply some shear forces on the underlying layers of fluid. So in this way, a shear force will be applied due to the friction among the two layers. So the friction force per unit area will be simply known as the shear stress, and it will be represented by tau. Experimental studies indicate that the shear stress for most fluids is proportional to the velocity gradient. So this is the velocity gradient. What does it mean? The change in the velocity with respect to the change in the y direction. So this tau, which is known as the shear stress, is directly proportional to the velocity gradient. And if we replace the proportionality constant with the equality sign, so we'll have to put some constant. This constant is known as nu. This proportionality constant is known as dynamic viscosity, and its unit are kilogram meter per second or pascal per second or twice. So the fluid that obeys this linear relationship, which is given here, that is the shear stress multiplied by the velocity directly proportional to the velocity gradient, this relationship is applicable to the fluids which are Newtonian fluids. I hope you have already studied about the Newtonian and the non-Newtonian fluids. And the best examples of the Newtonian fluids are water, air and gasoline, whereas the non-Newtonian examples are plastics or the molten plastics, and the blood are the classified examples of non-Newtonian fluids. So here an important terminology you will see in the process heat transfer when you try to solve the problems, that a terminology which is known as kinematic viscosity. So when you divide the dynamic viscosity by density, if you divide this dynamic viscosity with the density, and this terminology will be known as the kinematic viscosity. And viscosity is simply, that the resistance to flow, and it is a strong function of temperatures. So as you can see in this slide, in the upcoming slide, that the viscosity is basically changing with respect to the temperatures. In case of gases, the viscosities increases with increase in temperature, while in case of liquids, the viscosities in most of the cases will be in the decreasing trend, will have the decreasing trend. So the determination of this surface shear stress is not an easy task. So it required some practical knowledge, and it also requires the knowledge of velocity profile, and it is very difficult to determine. So we have some practical approach in an external flow which can correlate the surface shear stress with the velocity and the density and the friction coefficient. And this friction coefficient has no units. It is simply known as dimensionless. This is the more advanced way to determine the surface shear stress as compared to this expression, and this expression particularly applicable for the Newtonian fluids. It is not applicable for the non-Newtonian fluids. In order to apply this expression for the non-Newtonian fluids, we have to modify this expression. So this shear stress is simply the force per unit area. So if we replace this shear stress with the force per unit area, and the area from here will be multiplied on the right hand side. So this third expression is the extended form of this second equation. The friction force that can be used to determine when the fluid flows over a particular surface, and this is known as the friction coefficient. It is unitless. This AS is the surface area over which the fluid is moving. This is the density of the fluid and the velocity of the fluid. So the friction coefficient is an important parameter in the heat transfer studies, since it is directly related to the heat transfer coefficient and the power requirements of the pump or the fan. So that's why we will use this expression when we design the heat exchanger. So we will have to determine the friction coefficient, and from the friction coefficient we will ultimately determine the heat transfer coefficient. And heat transfer coefficient, as you know, that is one of the important parameters that we have already studied in the Newton's law of cooling. In this table, as you can see, that the dynamic viscosities of some fluids at 1 atm pressure and 20 degrees centigrade, it has different values from very small, that is here 0.000018, whereas the glycerine, which has 1.49 kilogram meter per second. So here is the general overview of different kind of dynamic viscosities of different fluids. You can just memorize for air and water and ethanol, or you will use these values when you design the heat exchangers. So you will need the value of the viscosity of different kind of fluids. So keep in mind that you are going to use this table. Now let's talk about the thermal boundary layer of a fluid which is flowing on a flat plate, and the fluid in this case, considering that, has the higher temperature as compared to the plate surface. So consider this is the flat plate, right, and it has a temperature of TS, and the fluid is moving from left to right, and the incoming fluid has a temperature of T infinity. Assuming that the T infinity is higher in temperature compared to the surface temperature. So as we have seen that the velocity boundary layer develops when the fluid flows over a surface as a result of the fluid layer which is adjacent to the surface will have the zero velocity, and similar is the case here, that the fluid layer which is adjacent to the flat surface will have the zero velocity. So the velocity boundary layers has a particular thickness, as I have discussed in the previous slide, that was represented by delta, and in this case the thickness of the thermal boundary layer will be represented by delta T. Delta stands for the thickness and T stands for the thermal boundary layer. This is a thermal boundary layer which is being developed when the fluid is moving on this flat plate with a specified temperature, and the thermal boundary layer is being developed because of the thermal gradient or the thermal difference between the temperature of this flat plate and the temperature of the fluid. So consider the flow of a fluid which is moving in this direction with uniform speed and a uniform temperature, which is T infinity, and consider that this flat plate will have the isothermal temperature, which means that this is at constant temperature Ts. So what will happen, the fluid particles in the layer adjacent to the surface will reach at thermal equilibrium with the plate, and assume that the surface temperature is Ts. So for example, this is the first layer which is near to the flat plate, and assuming that there will be the thermal equilibrium between this first layer of the fluid and the surface temperature. Both will have the same temperature, and there will be the thermal equilibrium. So the first layer, which is adjacent to the flat plate of the fluid, will have the Ts temperature. So the fluid particles will then exchange energy with the particles in the adjoining layer. So there will be the distribution of the energy in the normal direction or in the y direction. So this is x direction and this is y direction. So there will be the distribution of energy in the y direction. So what will happen? So heat will be transferred from the higher temperature to the lower temperature. So the temperature profile will develop in the flow field that ranges from this Ts surface temperature of the flat plate to the T infinity, which is the fluid temperature, which is far away from this flat plate. And this region, which is in the gray area, will simply known as the thermal boundary layer. And as I have already said earlier, that the thickness of this thermal boundary layer is represented by delta T. So the temperature at any point along the thermal boundary layer at any point will be determined by this expression. Considering that if we assume that the surface temperature is 0, so what will happen? So this Ts will be 0 and this Ts will be 0, and the temperature at this point or at the upper edge of the thermal boundary layer, that is T, will be equal to 0.99% of the fluid temperature, and it is the similar case as we have studied in the thermal boundary layer. So the thickness of the thermal boundary layer increases in the flow direction, as we have studied in the previous example in the velocity boundary layer. The thickness of the thermal boundary layer increases in the flow direction, and since the effects of the heat transfer are felt at the greater distances from the surface further down the stream, the convection heat transfer rate anywhere along the surface is directly related to the temperature gradient at any location. Therefore, the shape of the temperature profile in the thermal boundary layer dictates the convection heat transfer between a solid surface and the fluid flowing over it. In a flow over a heated or the cold surface, both velocity and thermal boundary layers will develop simultaneously. Noting that the fluid velocity will have a strong influence on the temperature profile. So the development of the velocity boundary layer relative to the thermal boundary layer will have a strong effect on the convective heat transfer coefficient. So thermal boundary layer and as well as the velocity boundary layers will be discussed parallel. So it will have a greater influence on the convection heat transfer coefficient. So let us discuss the next topic, that is known as laminar and the turbulent flows. If you have seen any person that is smoking, you probably have noticed that the cigarette smoke rises in a smooth plume for the first few centimeters and then starts fluctuating randomly in all the directions as it continues its journey towards the lungs of others, as you can see that in this diagram. Likewise, a careful inspection of the flow in a pipe reveals that the fluid flow is streamlined at lower velocities but turns chaotic or the turbulent as the velocity increased above a particular or the critical value. So the flow regime in the first case is said to be the laminar, characterized by the smooth streamlines and highly ordered motion, as in case of cigarettes or in case of the pipe flow. So in case of turbulent flow, in the second case, as you can see in this pipe, as you can see in this diagram, that if the fluid velocity becomes very high above a particular or the critical value, so the velocity fluctuations will be very high and the fluid becomes highly disordered. So the transition from the laminar to the turbulent flow does not occur suddenly. Rather, It occurs over some regions in which the flow fluctuates between the laminar and the turbulent flow when it becomes fully turbulent region. As I have already discussed this transition region in the velocity boundary layer, we can verify the existence of these laminar, transition and the turbulent flow regimes by injecting some dye streak into the flow of a glass tube, as we will observe that the dye streak will form a straight and the smooth line at a very low velocities when the flow is laminar. So consider this is a pipe and the flow is moving in this direction, right? The flow is moving in this direction. If we introduce a pink color dye or any pink color in this pipe, which is in which the fluid is moving in the right direction, so if the fluid is streamlined and the particles or the layers of this fluid in this pipeline is moving in particular speed and the fluid is streamlined, this particular dye color will also go in a straight line. It represents that the fluid which is moving in this pipe will be considered as the laminar flow. Whereas if we have a pipe, right, another pipe, and the fluid is moving from left to right, and if we introduce a particular color in this pipe, and we'll see that if the color will spread in all the directions, we can say that the fluid in this pipe is in the turbulent region. So we can easily identify between the laminar flow and the turbulent flow. A more elaborated picture of the velocity boundary layer in which three different regions are being labeled, and laminar, transition and turbulent regions, and the turbulent region has further three layers: the viscous sublayer or the laminar sublayer, the buffer layer and the turbulent region. I have already explained this diagram in the previous slide, but this is, I would say, the more elaborated diagram for the understanding of the velocity boundary layer. So the next topic is the dimensionless numbers in the heat transfer. In the convection studies, it is sometimes a common practice to non-dimensionalize the governing equations which is involved in the process heat transfer course, and to combine all the variables which groups together in the dimensionless number in order to reduce the number of total variables. So here we will discuss three different kinds of dimensionless number, that is the usselt number, prandtl number and the Reynolds number, and we will see that their definitions, their formulas and their prime importance in the heat transfer course. The first is the usselt number. The usselt number is named after the usselt who made the significant contributions to convective heat transfer in the first half of the 20th century, and it is viewed as the dimensionless convective heat transfer coefficient. So simply it is the ratio of convective heat transfer coefficient multiplied by some characteristic length LC divided by the thermal conductivity. To understand the physical significance of usselt number, consider a fluid layer of a thickness L and has a temperature difference delta T. It means that this layer has two sides. The one has a temperature of T1 and the other one is T2, and T2 obviously the higher temperature and T1 is the lower temperature. The heat will be transferred from T2 to T1, right, from higher temperature to lower temperature, and the difference will be similarly represented by delta T. Heat transfer through the fluid layer will be by convection when the fluid involves some kind of motion, whereas if the fluids in these two plates, right, is stagnant or motionless, so the heat transfer will be particularly by the conduction process. So the heat flux, what will be the heat flux? Heat flux is simply the heat transfer rate per unit surface area, and it is represented by this formula. So the heat flux is equal to H multiplied by delta T, and we also know that the formula for the conduction, that is given by this formula. If we take the ratio of the heat fluxes of convection and conduction, and after simplifying that, we'll have the ratio of H, convective heat transfer coefficient, multiplied by L divided by K, which is simply known as the Nusselt number. The Nusselt number represents the enhancement of heat transfer through a fluid layer as a result of convection relative to the conduction across the same fluid layer. So the larger the Nusselt number, the more convection process. As a result, if the Nusselt number will be equal to 1 for a particular fluid layer, so the heat transfer through that layer will be particularly by the conduction process. We have seen many examples of the convection process in our daily life. So we used forced convection in our daily life more often than we might think. So if we have the food that we want to eat that, and if it is hot, so we blow some air or by our mouth, so in order to cool it down. So this particular example is simply known as the convection heat transfer. So we are using the air in order to cool down this food that we want to eat. So we are forcing the air to flow over our food. So this kind will be known as the forced convection. So there are hundreds of other examples that we are using in our daily life that is particularly related to the process heat transfer. So the next dimensionless number is the Prandtl number. The relative thickness of the velocity and the thermal boundary layers is best described by the Prandtl number, and it is basically defined by the ratio of molecular diffusivity of momentum, which is represented by mu or small v, and the molecular diffusivity of heat, which is alpha. If we open these two parameters, we will have the viscosity, dynamic viscosity, Cp, the height capacity, divided by the thermal conductivity. So here we have a table that will give you the different values of the Prandtl numbers, that the liquid metals will have a very small value of the Prandtl numbers, and the gases will have the Prandtl number values are from 0.7 to 1, and the oils will have the highest value of the Prandtl number. So in case of liquid metals, the heat diffusivity is very high. So if the heat diffusivity is very high, so this ratio will become very small. So Prandtl number will be very small, right? So in case of oils, the heat diffusivity through the oils is very small. So if the heat diffusivity is very small, so this ratio will be very high. So as a result, that the Prandtl number for the oils will have very high. So the thermal boundary layer is much thicker for the liquid metals and much thinner for the oils relative to the velocity boundary layers. So the next dimensionless number is known as the Reynolds number. So it is very important to understand the physical significance of Reynolds number. So the transition of a flow from the laminar to turbulent will mainly depends on the surface geometry and surface roughness, the free stream velocity of the fluid, the surface temperature, as well as the type of fluids, and many other things are important when the fluid transition will occur from laminar to turbulent flow. After exhaustive experiments in 1980s, the Reynolds discovered that the flow regime depends mainly on the ratio of inertial forces to the viscous forces. So the ratio of these two forces, the inertial forces divided by the viscous forces, is simply known as the Reynolds number, and it is also a dimensionless quantity. Let us try to understand or to develop the expression for the Reynolds number. For example, this V is known as the upstream velocity, which is equivalent to the free stream velocity u infinity that we have studied in the velocity boundary layer. This L or the LC is the characteristic length or the geometry over which the fluid is moving, and this mu will simply known as the kinematic viscosity, and it is the ratio of the viscosity, dynamic viscosity divided by density. If we replace this with the ratio of mu over density, so if we open this, we will have this expression. So the derivation of the Reynolds number is given here. I would simply say that the students must go through this easiest derivation for the Reynolds number. So the physical significance of the Reynolds number is very important. For example, if the Reynolds number is very high, what does it mean? The inertial forces in this ratio would be very high. It means that the Reynolds number are proportional to the density of the fluid and the velocity of the fluid, and the viscous forces are very small in case of very large Reynolds number. On the other hand, if the Reynolds number is very small, in this case the viscous forces are very large enough to overcome the inertia forces and in order to keep the fluid in line or the straight line. We can simply say that if the Reynolds number is small, so the fluid will be in the laminar region. If the Reynolds number is very high, the fluid will be in the turbulent region. The Reynolds number at which the flow of the fluid becomes turbulent is called the critical Reynolds number. The value of the critical Reynolds number is different for different geometries. So let us take an example of the flat plate in which the critical Reynolds number value is 5 multiplied 10 raised to the power 5. After that, the fluid will turn into the turbulent region. The value of the critical Reynolds number may change substantially, however, depending upon the level of turbulences in the free stream.